Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at two sets of differentiation rules that we have already discussed in one of our videos. And these are going to be very important, especially that we are doing or maybe trying to use this concept of differentiation and integration in some of the aspects of mathematics and physics. So for that case, thank you and welcome. So for today, our topic of discussion will be just try to have a look at two specific rules that we use for differentiation, and that's the constant function rule and the power function rule. We had promised in our previous video on differentiation rules that we're going to look at two different sets of functions at a time for differentiation, and in this case we're going to use a graphical representation to try and of course define or maybe explain on what these basic rules entail. So in that case, I'm going to start with the constant function rule. So basically this stems from the differentiation rules. And first we're going to look at the concept of a constant function rule. And this is going to assist us to interpret some of the aspects in physics, maybe when it deals, when it comes to the concept of maybe motion in made two-dimensional space, maybe or linear motion, etc. Now suppose I have a graph which of course is a function of fx or y against x, which has got a function that is a, then a can be represented as fx is equals a. Now the change in the x-axis at maybe from the point of origin from this point P to Q will be represented as delta x. And this now therefore is going to form a basis for a short discussion. Last time we said that the derivative of a constant function fx, so therefore I can just give this one in the form of a short statement. The derivative of a constant fx equals a, where a is a constant is given as f prime of x, which is equals to 0. So basically from the power rule we try to look at how we can be able to find a differential or maybe a derivative of a function, and we said that if the function is given as x to power n, then the d xn over dx is given as n xn minus 1. So therefore we're going to use this particular concept and just going to give a short illustration for that. Now from the power or the indices, we know that when a number a is raised to power 1, it's the same as a. But when a number a is raised to power 0, this is given as, no, this is just given as 1. So a number raised to power 0 gives 1, or to the exponent of 0 gives 1. Now if we are trying to do this differential using the power rule, then we can say that fx, that is f prime of x, is given as, if this a was initially given as, alright, in this case this function can be given as a to the exponent of 1. So a number to the exponent of 1 is that number, so that's why maybe it's just given as such. But if we are trying to do a differential for this, it's 1 minus 1, and then it's going to give us a 0. Of course this one is going also to come here, so this is going to be just 1. So therefore the derivative of just a function which is given as a is a constant which is given as 1, which can be represented as 1. Now in this case, if we have written the f prime of x is equals to 0, this is a derivative from the concept of a slope that I had given. Of course, this is going to indicate that in this case, we're just trying to differentiate this number with respect to x, where we have a raised to power 1 x raised to power 0. So this exponent, whenever a number is raised to power 0, of course it's the same as 1. So if we bring this particular exponent in this particular part to be just like a coefficient, we're going to have this number still given as that, which will give us 0. So let's maybe trying to expand on that constant function rule. And next we are going to look at the concept of the power function rule, which we have partially mentioned in trying to explain this constant function rule. So for the power function rule, we say that the derivative of a function fx given as x to power n, where n is a positive integer, and in any case, of course, it can just represent an arbitrary constant. So the procedure for us in trying to find the derivative of this particular function, we said, therefore, or implying f prime of x will be given as n x n minus 1. So that's a general representation for trying to find the derivative of that function. Now there are specific conditions which we are going to see, which are going to affect the graph of this specific function. So in comparison to the graph of this function and the graph of its derivative, we're going to see that in a case where n is greater than 1, the derivative of the function just a minute. The derivative of that function will be a function which will be increasing, and we're going to see that one using a graphical representation. Now in this case, if we have a graph of a function of fx, raised to the power of n, where n is greater than 1, we're going to have an exponential graph, which we can be able to represent as just like that, where this is f of x, y-axis against x. So in this case, if our function was, we can give an example of x 3/2 being our f of x. Therefore, its derivative f prime of x using the power rule is going to be given as 3/2x 3/2 minus 2/2, which is basically 1. So therefore this is going to give us 3/2x, and this is 1/2. So x 1/2. Now the derivative, the function of this particular derivative is going to give us a graph of this nature. So this will be f prime of x against x, and then we are going to have a function that is behaving like that. So we say that this, when n is greater than 1, basically, which is an exponent, this is 1.5, so it's greater than 1, the f prime of x, which is our derivative, is going to have an increasing function, which is going to behave like that. So that is scenario A. We're going to have another scenario for B, where maybe we find n behaving in a different way, and try to define, maybe try to illustrate how its function, which is a f prime, is going to behave. So suppose we have n, we've already discussed about this under the constant the constant function rule, but we just have a mention it. Suppose n, this is x, this is a function fx, which is given as xn. Now suppose n is equals 1, from the constant function rule we say that the derivative of a function will remain constant and will be equal to 1. So therefore, suppose this is n is equals 1, so n number raised to power 1 will just be the same as that, so therefore this one will imply a constant. And if we try to give a graphical representation for this kind of a function for that condition, then we are going to have a function, for example, of or just a function being represented as fx is equals x. The graph for that specific function of fx against x will just be a constant, which is fx is equals x. So in that case, it's the derivative, which is f prime of x, is going to be a function that is going to behave such that's a negative exponential function. So we said that this kind of a just a minute, there's a hitch somewhere. So we said that this is going to give us a constant, and therefore the f prime of x is going to give us a function which is going to be a constant of that nature. So this is f prime of x is going to give us a function. Now this is for the case where n is equals 1. Now suppose n is smaller than 1, then we can as well, so this was scenario B. Now we're going to see the last scenario for n smaller than 1 and try to see using graphical representation on how the derivative of that function is going to behave. So suppose n smaller than 1, we can have an example of a function like f of x is equals x raised to half, and implying its derivative f prime of x can be given as a half x and half minus 2 over 2, which is going to give us a half x. This is minus 1 over 2. So that's going to be its derivative. So for the function fx against x, it's a graphical representation for that. We're going to have a graph of fx, which is fx, x, half. So this is going to have an f prime of x given as, so this is f prime of x given as that specific graph. So we just said for this condition the derivative function will be a decreasing one. So the first one was the derivative is decreasing. Now for the second condition where, for the first condition where n was greater than 1, of course we saw that there was an increase. Let me just use this for illustration. We make a correction on that in case we're just given a wrong representation. So for that case, in comparison with the function where n was greater than 1, we said its exponent or the graph was to behave as such. So this was fx is equals 3, is equals x 3 over 2, and then its derivative on the other side will have been a graph behaving as such, and that one was f prime that was f prime. Okay, that 3 over 2x half. So this gives the difference between an increasing and a decreasing function, whereby we have seen the one in black, the derivative of the function where n is smaller than 1, we're going to have it as a decreasing, for the function of that derivative as a decreasing one. And for fx, where n, this is this, for the blue representation, this is where n was greater than 1, n greater than 1. And this for this other one for black, for representation for black, this is where the case where n smaller than 1, n smaller than 1. So I hope maybe there was a confusion in between. That one will act as our point for correction. So in this case, having looked at those specific differentiation rules, they are going to assist us in trying to define some of the functions that we may come across, or maybe graphical representation of data, maybe in physics or mathematics, in graph work that we may come across, which is trying to give this specific behavior. So maybe this is going to give us some of the clues about the decreasing and increasing functions, and therefore we can be able to interpret whether entity or a phenomena that is under study is either increasing or not. This one we find, of course, some of the applications as I've mentioned in topics like radioactivity and maybe decay processes, etc. So that we'll stop there for today. We are remaining in two sets of course, differentiation rules that we're also going to handle as a set, so that we can be able to finish on this and work on other sample questions regarding differentiation. So that is it for today, guys. Bye, God bless.